Alright, so let's get started then. First thing about HVAC, we have to discuss some theory. There's some thought process, some science we have to uncover to really understand how everything's working. So first, what we're going to do today, before we get into our tablets and the online book and all that, we're just going to take some basic notes, break down some theory, so that you understand what we're talking about. Then when we do get into the book, it'll make a lot more sense. First question I have. What is hot and what is cold? For you, sir, what's hot and what's cold?
Water.
Water? Okay. For you, what's hot and what's cold?
High temperature or low temperature.
Okay. What about you?
Summer, winter.
Summer, winter, okay.
Heat and lack of heat.
Heat, lack of heat, okay. What about you? To you, what's hot and what's cold? There's no wrong answer.
Summer out here and winter in Colorado.
Okay, good. What about you?
Same thing, high temperature and low temperature.
Okay.
85 degrees is hot, 68 degrees is cold.
All right, I like what you think. Yes.
Same high temperature, low temperature.
Okay. What about you, sir?
Furnace, air conditioner.
Okay.
The difference in the circumstances that determine the type of molecule.
Oh, going deep. I like it. What about you?
Say summer, winter.
Summer, winter. Okay. What about temperature-wise? Can you think about what's hot for you? What's cold for you? Have an idea in your
I'll
head?
stick to my answer.
So first, we got to determine what is hot. Hot or heat is really a type of energy. I need to make a clarification. I'm the worst speller that there possibly is that you'll ever meet. I'm really good at HVAC, but I'm a horrible speller. I misspell 90% of everything I write, so when I'm just trying to get the ideas out of my head onto the board. So don't write it word for word. If it's spelled wrong, just go ahead and correct it in your paper. Make that little clarification. So heat is energy. And we have to go down to the basic molecules. Everything is made of atoms. And you can't trust an atom because atoms make up everything. Lots of lame jokes also. So everything's made of atoms. This table's made of atoms. We are made of atoms. The air around us right here is made of atoms. Everything's made of atoms. And these little bitty atoms come together to make molecules, and these molecules are in motion all the time. There's electrons moving around this table. Looks solid, right? It's in motion. All of the atoms and molecules are in this table are in motion. They're moving. To us, it feels solid, but in reality, they're moving. As we add heat energy, those molecules move faster. They start moving quicker. If we add enough heat energy to things, we can melt them. If I add enough heat energy to this plastic, the plastic will start moving so fast it will turn to liquid. Does it make sense? So it's all in motion. If I add heat energy, the molecules move faster. If I reduce heat energy, the molecules start to move slower. All right, so far so good? All right, so that's what heat is. Now let's talk about what cold is. All right, so cold. Here's what cold is. And it's not that we have to memorize this, but it's a very important concept for us to understand. Cold is also known as, put this way first. There's actually some decimals there, but for our sake, we'll just keep it simple. Minus 460 degrees Fahrenheit. Minus 460 degrees Fahrenheit. That's cold. It's also known as minus, I don't know what it is in Celsius, 273, I think. I could be wrong. 273 degrees Celsius. It's also known as 0 degrees Rankine and 0 degrees Kelvin. And I heard somebody say it, which is fantastic, right on point.
Absolute zero.
Absolute zero. Absolutely correct. Absolute zero. This is where all molecular motion stops. Where all molecular motion stops. That is cold. Defined, without a doubt. So, can anybody tell me what color this plastic is?
Clear. Transparent.
Clear, transparent. If you go and buy colors or go name the colors of the rainbow, is clear one of the colors?
Nope.
No, clear just simply represents a lack of color, right? Kind of weird, right? But clear isn't really a color. It's lack of color or absence of color. There really and truly is no such thing as cold because we cannot obtain absolute zero. We can get within a fraction of a degree, but we cannot obtain that. So there really is no such thing as cold. Cold is just simply another word for absence of heat, lack of heat. Okay, so far so good? It is a very important concept because when we're going to be looking at things, we have to look at things a little differently. For example, minus 459 degrees Fahrenheit. Would that be considered cold?
No.
No.
No. Oh, good. You guys are rocking it. Yeah, that's correct. There is 1 degree of heat. There's 1 degree Fahrenheit of heat there. So that is heat. There is heat there. At 0 degrees Fahrenheit, would that be considered cold?
No.
No, because at 0 degrees Fahrenheit, here's our cold spot, minus 460. And here's 0. There are 460 degrees of Fahrenheit of heat at 0 degrees. Interesting, huh? So, I know right now, like, what are we talking about this for a bit? It's going to come together. I'm going to have a lot of little pieces I'm going to give you, and then they're going to start coming together more and more. This is a very important concept for us to understand because we're going to be building off of this. First, we have to understand what is hot, what is cold, and we're going to be using cold a lot, but usually you'll see me when I say the word cold, I usually put it in quotations because I'm really not talking about true cold because that would be minus 460. Usually I'll say something like, there's a lack of heat in the air. It's what you guys would call a cold morning of, oh, there's a lack of heat outside. Because it's the thought process of where we're going. Right, so far so good?
Yep.
All right, it's good. All right, then let's talk about thermodynamics. Thermodynamics. Thermo, anybody know what thermo means?
Temperature.
Temperature, heat, yep. Temperature or heat. And dynamics?
How something operates or reacts.
Yes, how it operates, how it reacts. That's exactly right. Dynamics, what makes it work, how it works. So everything we do in HVAC is all about thermodynamics, how it works. So how heat works. So some people in HVAC don't like to call themselves HVAC professionals. They like to call themselves thermodynamic professionals. Same thing, but it just sounds cooler, right? Some of the people you talk to, they're like, I don't know what you're talking about. That's fine. Thermodynamics, the study of heat and how heat works. And in HVAC, whether we use the big fancy title or not, we have to be thermodynamic experts. We have to understand how heat works. And we have 2 laws that we have to worry about. The first law, law number 1, is energy. Energy cannot be created nor destroyed, only transformed from one form to another. Energy cannot be created nor destroyed, only transformed from one form to another. What's another word we can use to replace the word energy?
Atoms. Well, molecules.
You on the right path? Keep going.
Movement of molecules.
Yes, movement of molecules. What's a word that we can use to sum up movement of molecules?
Transferring of electrons.
Heat. Heat.
Oh, yeah.
So energy cannot be created or destroyed, only transformed from one form to another. And really and truly, we could replace this word with heat. Heat cannot be created nor destroyed, only transformed from one form to another. Okay? So there's many kinds of energy. Electricity is a form of energy. Water, taking water up high and letting it fall, energy. You have potential energy, you have kinetic energy. There's tons and tons of type of energy. We have food energy, chemical energy. When we burn fuel, when we eat food, that's a fuel that we're burning, our bodies are burning. All of those are types of energy. We can't destroy energy. We can transform it from one form to another. I can take one type of energy and turn it into electricity. I can take electricity and turn it into heat. I can take heat and turn it into electricity. There's many things we can do to change it, but we cannot destroy energy. In other words, we cannot destroy heat. We can't destroy heat. So in HVAC, if we want to cool the house, we need to do that, but we cannot destroy heat. Right? So basically what I'm trying to say is our air conditioner does not make cold air. Because to make cold air, it would have to really be destroying heat. The destroying heat means I have to destroy energy, and the first law of thermodynamics says you can't destroy energy. Right? So far so good. And on that little topic, we'll take a little side note. You'll see on YouTube, there's all these people have perpetual motion devices that just go on forever and ever and ever, which is just not possible because you have friction and you cannot make free energy. You can get energy from one source to another. Our biggest source of energy is the sun. Massive amounts of power come from outside the planet that we have to work with, but we cannot create energy. We cannot destroy energy. We can only transform it from one form to another. The biggest waste of energy we end up with is heat that dissipates outside of our planet. Okay, so far so good. All this really says is we can't destroy heat. And just so we know, you'll see this again later in other classes or in a book. This is also has another name defines this as well, and it's called Law of Conservation of Energy. The law of conservation of energy is also the first law of thermodynamics. Why did they have to give it two names? I don't know. I guess it was just that good of the information that they figured that they give it two names. The law of conservation of energy and the first law of thermodynamics. Heat cannot be created nor destroyed, only transformed from one form to another. Alright, so let's continue on. Second law of thermodynamics. There's actually many laws. We're only concerned about the two. We're going to keep it to the most important. Does anybody know the second law of thermodynamics? It's not a problem. I'm just going to say how the first one is. Heat from a more abundant source travels to a less abundant source. Heat from a warmer area travels to a cooler area is a better wording for it. Heat from Heat from a warmer area travels to a cooler area. Notice I said cooler, not cold. Heat from a warmer area travels to a cooler area. Heat from a warmer location travels to a less heated location. There's tons of ways to word it. The most common way you see this worded is this. Heat seeks cold. Notice what I did with cold? Quotations, because it doesn't just seek minus 460 degrees Fahrenheit. Heat seeks areas of less heated, or cold in quotations. So far so good? Heat seeks cold. This is extremely important. If we want heat to move, I have to trick it into going to something that's less heated. So far so good? Alright, so now let's tie this into air conditioning. We can't destroy heat. We can't make cold. So what we have to do is move the heat. So what we have to do in the house, if it's warm in this room, I have to get the heat out of this room. That means I have to take heat energy from inside and I have to dump heat energy outside. Make sense? Mm-hmm. To get that to happen, we have to trick it. We have to get it to go into something that's less heated or something that's cooler. So that's what we're going to use as our evaporator coil or inside coil, and we're going to use refrigerant. And we're going to make that refrigerant a lower temperature than the air temperature. And if the refrigerant's a lower temperature and the air temperature is warmer, will the heat want to travel?
Yeah.
Yes. The heat will leave the air and go to the refrigerant. Now what happens to the temperature of the air? If the heat's leaving the air, what happens to the temperature of the air? It gets cooler. The temperature drops. Now the heat's in the refrigerant. But I got to get the heat out of the refrigerant. So I have to take that refrigerant outside. I have to manipulate it. And I have to get the heat to leave the refrigerant. And so some things we have to do, especially in this topic here today, to make that happen. And then once we get the heat out of the refrigerant, we can go back inside, absorb heat from inside, take it outside, dump the heat outside. That's what we're going to be doing with the air conditioning, refrigeration. So far, so good? Any questions yet? No? Okay. All right, so got a little experiment for you. Try. We have two things in this room. Now don't call the answer out loud. I want everybody thinking about it. I want to pass this around. You feel that quickly, grab this quickly. Don't hold it, just grab it quickly, grab that one quickly, and then pass it around. And think about which one was warmer and which one was cooler. All right, so which one was cooler?
Same.
Most people said the copper was cooler, but in reality, they're both the same temperature. What? It goes back to the second law of thermodynamics. And we can talk about it, but until you actually apply it, it doesn't make a lot of sense. And here's why. Anybody know what your body temperature is?
98.6 maybe.
Approximately, yep. Every person's a little different. And the temperature of this room is 70 degrees Fahrenheit. So the temperature of this room means everything in this room that's not creating heat is 70 degrees Fahrenheit. Both of these items, slightly different location, but the same height in the room. The copper and the back. The difference is the copper conducts electricity and it also conducts heat very fast. Your hand is warmer than the copper, right? Mm-hmm. So the heat from your body is traveling to the cooler copper. So what happens to the temperature of your hand? If the heat's leaving your hand going to the copper, what happens to the temperature of your hand? Your hand gets cooler. And you perceive that as being cooler. Now, this is also the same temperature, except it's insulation. It doesn't resist the flow of heat. It doesn't absorb heat as quickly. So when you touch this, heat's still leaving your hands, but at a much slower rate. So that means your hand isn't cooling off as much. So when you touch this, it feels warm, right? That's the second law of thermodynamics. So what we use to make heat move into is important. We use insulation to slow the transfer of heat, and we use conductors to speed up the transfer of heat. So if we think about air conditioning refrigeration, I take heat out of this room, but once I get the heat outside, what's it trying to do?
Get rid of it.
It's trying to come back in. It says, hey, it's cool inside, let's go hang out in there. So if we take heat outside, it's trying to come back in. And this is what's important. In our walls, we have to put insulation. If we put insulation in the walls, once I get that heat outside, that heat's trying to get back in, but that insulation slows it down. It's still moving in, but it slows it down. If you've ever been into a metal box in the middle of summer, you can really appreciate that. One of those metal sheds, summertime baking, a lot of heat transfer very quickly, and it gets very, very warm inside that box. But if it was possible for this just to be colder, we wouldn't need air conditioning. We could just put copper pipes in here and the heat would just magically go to it. We could cool the house off. But in reality, it's the second law of thermodynamics. Your body temperature is warmer than the copper, so when I touch the copper, the heat's leaving my hands, temperature of my hand drops, I feel it being cooler. But the same thing applies in the summertime. If I was to set this pipe outside that sidewalk out there, middle of June, and then go and touch it, is it going to be cooler? No, it's going to be the same effect, but in reverse. I can take both of these pieces, put them outside in the sunlight, let them absorb some heat energy from the sun, go and touch it. This one now is going to feel cooler because it's resisting the transfer of heat. And I touch this one and it's going to be, ow. There's a fast movement of heat from that copper into my hands. Okay? Second law of thermodynamics, it works both ways. In the wintertime, we heat the house. So we're putting heat into the house. And what's that heat trying to do that's inside the house?
Leave that.
It's trying to leave. It's trying to go to the cooler spot. Heat's, it always wants to hang out with the cooler areas. It's like, hey, let's go hang out with the cool kids. So we heat this room, the heat's trying to leave. It's trying to go outside because there's a temperature difference. It's always seeking the cooler area. It's always wanting to go to where the cooler party is. Any questions yet? Is it interesting?
Yeah, it's like a hot girlfriend.
Always looking for the guy with more money?
Yeah.
Right? Now there's two things that affect the speed of this. The speed of this. One being surface area. The surface area. All right, so let's apply this to where it might, see if it makes more sense. Let's say that you have a pie, and the pie is right out of the oven. And that pie is nice and hot. And I put that pie into this room. What's going to happen to that pie over time?
Cool.
It's going to cool off. The heat from the pie is going to go to the cooler air around it. The air will warm up, the pie will cool off, and eventually they will equal out. Does it make sense? Eventually, that's what's going to happen. Now, if I took two pies, brought one out of the oven, had it right here, and I took the other pie and I cut it up into a lot of areas and separated those areas out, cut it up into those small pieces, which one will cool off faster?
Smaller pieces.
The smaller pieces. Why?
Surface area.
Surface area. It's exactly right. There's more air touching more of the pie. When the pie is all together, it's only touching the outside edge. But when I cut the pie up, now the air is touching the top and the sides and the bottom, the tops, the sides, and the bottom of this piece. There's more air touching more of the pie. So the surface area is going to affect the speed of the second law of thermodynamics. Same thing with a radiator. If your engine on your car is hot, will it not give off heat to the air around it?
Yeah.
Yes, it will. But if I take that heat, put it in the water, run that water through a whole bunch of copper, we've extended the surface area, And then on that copper, I put aluminum fins up and down, up and down, up and down. I've made the size of that engine touching the air multiplied many, many, many times bigger. I have increased the surface area. And by having more surface area, there's more air touching more of that water, more of the water touching more of the engine. It makes that engine much more effectively cooled because of surface area. This is very important for air conditioning as well. If I want heat to leave the air and go into the refrigerant, I need more refrigerant touching more of the air. And we're going to see this today. It'll make more sense. So we want more of the refrigerant touching more of the air, and I can speed this up. Both pies will cool off, right? Which one's going to cool off faster? When it slides, when it has more surface area. So I could take refrigerant, run it through this tube, and push air across it. And if the refrigerant's cooler than the air, the heat's going to leave the air and go to the refrigerant, yeah?
Yep.
But if I took this pipe and doubled it, would I speed that up? And what if I did it again? And then again? What if I took this big pipe and ran it into a whole bunch of little bitty smaller pipes? There's even more air touching even more copper, which is touching even more refrigerant. Would that speed that process up?
Yeah.
Absolutely. Yes, it would. So we want to have more surface area. And the same thing outside. We have the refrigerant that's going to be running outside this building. And I want the heat to leave the refrigerant and go to the air. Would more surface area make that happen faster?
Yes.
Yes. Surface area. So there's two things that affect the second law of thermodynamics. Surface area and, do you have a clue? Any ideas?
Compression.
We can manipulate temperature with compression. What we're looking for is temperature difference. Temperature difference. The bigger the temperature difference, the faster the heat will move. The bigger the temperature difference, the faster the heat will move. If you ever notice you had something really hot, it cools down really fast, and as it gets cooler, it takes longer for that last little bit to go. And when you get down to where it's only like 3 or 4 degrees above the temperature of the air, it's still cooling off, but it just takes longer to get there. Anybody noticed that before?
Yep.
Seen it? And it has to do with temperature difference. The bigger the temperature difference, the faster the heat's going to move. It's kind of like pressure. If you have if you add more pressure to something, it's going to leak out faster, like a tire. If you got a tire that's fully inflated and you have a nail get in it, and you can hear the air coming out of it, and it starts going down real fast. And then as the pressure difference between the inside and outside is less, it starts going down less and less and less. Same kind of thing, but heat works that same way. The bigger the temperature difference, the faster the heat moves. And here's an example of how it applies to air conditioning. Let's say that inside this room is 70 degrees, and outside this room is 72 degrees. And I want to keep this room at 70 degrees. I got to take heat out of this room, right? I take heat out of this room and put it outside. 72 degrees versus 70 degrees. Is it going to maintain its temperature pretty well?
Yeah.
Is there still going to be heat transfer?
Yes.
Yes, the heat still wants to come back inside, but it's only a few degrees warmer. It's not going to be moving very fast. It doesn't have a big drive to get back in. Same scenario, 70 degrees in this room. It's 115 outside. Is there a bigger temperature difference?
Yes.
Is that going to affect the second law of thermodynamics?
Yes.
Yes. When it's 115 outside, there's a whole lot more heat outside than there is inside. The temperature difference between outside this room and inside this room is massive. So the heat from outside is like, hey, we got to get in. And the heat starts fighting its way through the walls, through the windows, through the floors, through the ceilings, and it starts pushing back in because there's a huge temperature difference. And that big temperature difference means there's basically more pressure, more push. The heat's being pushed in at a much faster rate. Make sense? Both of these, everything we work with affects both of these. And in the summertime, when it gets extremely, extremely hot outside, lots of heat in the air, second law of thermodynamics plays a part in it. The temperature difference, a big effect in it. Okay? Any questions yet? No? Did you know that there's going to be so much in the HVAC? It's important to understand how something works. If you understand how something works, you're much more likely to be able to fix that. But if you don't understand how something works, doesn't mean you can't fix it. It just means it may not find the main cause, the main problem. Yes?
Alright, so for example, my body's 98 degrees. My sweater's the insulation, and the heat tries to get into it to cool me down if it's 60 degrees outside. So the heat, the heat's leaving my body.
Yes, that's right.
So the heat is leaving my body, and the insulation is the only thing keeping it.
That's exactly right. It tries to slow the heat transfer. So when you add more jackets on, what it's doing is trying to hold the heat inside. You're trying to slow down the second law of thermodynamics. You're trying to reduce surface area, and you can't change the temperature difference, but by reducing the surface area, adding more insulation, you're slowing that process down. And our bodies are engines. We're creating heat. And that's why you can't put jackets on to stay cool in the summer, because we're putting heat off massively all the time. And it goes back to how our body cools. That second, the first one here really plays a big part of that. If you have a fan on you, you're moving more air across your body, so there's more molecules of air touching your body, so it makes you cool your body off much faster. And the same thing goes in wintertime. When the wind's blowing in wintertime, it feels much cooler because it goes back to the surface area. There's more air, molecules of air touching your body as it moves through you, through your clothes, and it has a bigger effect on how your body is cooling. And it feels much cooler, which they call wind chill factor. The chill of the wind. Yes, that's the thought process we need right there. Insulation, trying to reduce surface area, we can't change the temperature difference, but we can, knowing how that works, we can control those effects. All right? Any other questions? Good question. No? We're all on track? So far, so good? All right. So, let's get into how it's working. So the refrigeration cycle, let's talk about how we get this to work. So we're going to have a refrigeration cycle. And we're going to start with a component. I'm also not an artist. There's one component that really makes everything happen, and this is called a compressor. And everything in HVAC has at least two names. So there's two words we have to learn for every single thing. So compressor is the most common word, but it's also called... Yes, sir?
Is that the schematic symbol for compressor right there?
No, it's just my drawing symbol. It's just a horrible... When we get out to the lab, you'll see what I'm trying to... In just a minute, we'll take you out there, and I'll show you what I'm trying to draw so you'll understand.
Okay.
But for now, it's just compressor, and it has two words. One word is compressor. The second word is a vapor pump. A vapor pump. Vapor also meaning gas, is like gas in the air, vapor in the air. Vapor pump. Can it pump a liquid?
Sure.
Yeah.
No. Because it's a vapor pump, it can only pump vapor, it can only pump gases. It cannot pump a liquid. And the reason that is you cannot compress a liquid. You can sling a liquid, you can push a liquid. Liquid pumps, they're really not pumps, they're actually centrifugal. With a centrifugal pump, it's actually slinging the liquid. But when in a vapor compression system, you cannot compress a liquid. And a vapor compressor, the word compressor means it's compressing it. It's taking it from a large volume into a smaller area. And when you compress it, if you try to compress a liquid, you might know what you get when you try to compress a liquid? You get hydraulics. And that's how they're able to make all that equipment move, dig massive holes, all that's from hydraulics. You cannot compress a liquid. You can compress a vapor, you cannot compress a liquid. So air compressors, we take all these molecules in the air, we can compress them down into a small tank, we can increase the pressure. But a liquid, if you have a big jug of liquid and try to squish that liquid,
It goes.
either it's going to break or it's not going to squish at all. I mean, one of the two. If you have try that when you get home. Take a water bottle, fill it up completely, and try to squeeze it, and it just pushes out someplace else. That's why the cans of soda, when you buy those cans of soda, it's one reason they also add a little bit of gas in there as well. But they're able to hold so much weight, they're able to stack them so high because you cannot compress that liquid. It holds their shape very well. If we get liquid into this compressor and we try to compress it, something will break. Same thing with a car. If you ever have the car and you say, if you ever get it in water, don't shut it off, it'll suck that liquid up in there, and as the engine tries to compress that liquid, it cannot, and something will break. Think about a cylinder. Oh, that one's bad. 2 down, 1 day. Okay, we got a cylinder here. Bottom's going to be open, and we have a piston. And we got valves open and closed. But if we fill this cylinder full of air, and on the compression cycle, this piston goes up. What happened to my volume here?
Compressed it?
My volume decreased. I have less volume. So what happened to my pressure right here?
You went up. Right?
Increase, massive increase. So when your pressure goes up, you're taking all that molecules of vapor and you're pushing them together in a smaller area, and you're going to have higher pressure. So when this valve opens, it's going to allow gas to escape. On this side of an intake valve, and as I increase my volume, it makes a suction and it pulls gas in. In this case, we compress it, pushes it out. And that's why on the muffler, on the exit of your tailpipe, it's always pushing out because the gas is escaping in a smaller area. Now, if I tried to fill this with liquid, it's non-compressible. All right? And I try then on the cylinder to push it forward, and you cannot compress this, what's going to happen?
It's going to crack the piston or break something.
Something will break. It's going to be this rod here, something in here, the valve, something has to give. And we don't want that to happen. So in HVAC, we deal with these compressors, and what we want to do is make sure that we never get liquid in there because it will break, without a doubt. So vapor, only vapor, 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 no liquid. The job of this compressor, it's got several things. One of its jobs is to simply move the refrigerant. Right? It's going to move the refrigerant. We're going to have refrigerant inside the system, and it's going to make it move. And simply by doing this, it sucks low pressure vapor. So going in is going to be low pressure vapor, and going out is going to be called pumps, a high pressure vapor. So going in is a low pressure vapor. Going out is going to be what?
High pressure vapor.
High pressure vapor. So there's going to be two pipes. The bigger pipe going in is going to be the low pressure vapor pipe. The smaller pipe coming out is going to be the high pressure. Keep it in, to keep all that contained under high pressure, we need a smaller pipe. Keep it all pressurized. So far so good? All right, let's go to the lab. Let's show you what a compressor is so you have an idea what my horrible little drawing is supposed to be.